Hello, everyone. We're going to get started in a few minutes. I think everyone is here now. We're going to start with session 10 now.
I'm vertically challenged, so I need to fix it. Hi everybody, welcome to session 10. This is the last presentation session for the symposium. And so before we start, can I just get a whole round of applause for Lauren and Maddie, fearless leaders planning the symposium. So we're finishing strong. We've got 6 speakers lined up for you this session. The session is titled Technology and Innovation in Marine Debris Monitoring and Removal. So our first speaker to kick us off is Ali Ebrahimian, and his talk is titled AI-Powered Characterization of Solids and Microplastics in Stormwater Runoff and Their Mitigation via Green and Gray Infrastructure in Urban Coastal Areas. Take it away, Ali.
Hello, everyone, and thank you for having me here. This is kind of a new project. We just started, like many of you, a couple of months ago. So I'm going to be just providing some overview and our plans for the next 3 years. Next slide, please. By the way, my name is Ali Ebrahimian. I'm from the Department of Civil and Environmental Engineering from Florida International University down in Miami, Florida. So I'm pleased today to present on behalf of a really interdisciplinary team, including Dr. Anna Braswell from Florida Sea Grant, Professor Cinto from our Department of Earth and Environment, Professor Gardinelli, Department of Chemistry and Biochemistry, Dr. Watanka from Environmental Engineering, Dr. Pulizo and Dr. Lu, both from Computer Sciences. We have 2 industrial partners, Tetra Tech and 3 sources that are part of our team, and the whole team is being supported by an extensive technical advisory panel, including multiple state, regional, and local government organizations, mostly in South Florida, and for the state is for the state of Florida. Next slide. So I'm going to be talking about stormwater today, and by stormwater runoff, I mean the portion of rainfall that is running off the surface after a rain happens. And that stormwater runoff is a major pathway for anthropogenic debris, including total suspended solids and microplastics from terrestrial environments, urban areas, through our stormwater management infrastructure, including storm sewer systems, all the way to our oceans. And despite the fact that that's a major pathway for sending our pollutants to our receiving waters, this area is understudied. And probably one of the main facts is because there is not enough data on the contribution of stormwater to microplastics in oceans. And part of that is probably because we don't have simple solutions, simple monitoring techniques, simple measurement techniques. A lot of our analytical chemistry methods are time consuming, and they cannot meet the requirements of a high throughput, long-term microplastic monitoring program. So we are looking for some simpler methods, rapid methods that can meet those requirements. On the other hand, in terms of solutions, currently we have some sort of nature-based solutions for stormwater management. We call them green stormwater infrastructure in urban areas. Those are practices such as rain gardens, bioretention systems, constructed wetlands, bioswales in urban areas that can be used for addressing stormwater quantity and quality issues while providing a wide range of ecosystem benefits. Recently, there have been some studies for the performance of these green infrastructure for microplastic removal, but there's a lot more study. There's a need for a lot more study in this regard. So with that background, next slide, please. Here are our objectives. We're going to be assessing the performance of both green and gray. Gray infrastructure are just traditional storm sewer systems. the performance of green and gray stormwater infrastructure for the generation and mitigation of TSS, and TSS is total suspended solids, and microplastics, MPs. The stormwater runoff, we are planning to develop, to use our data and develop an AI tool for MP characterization. Also, we are planning to develop a decision support tool that can help with improving the performance of these systems. And finally, we are creating an outreach and education plan. Next slide, please. So we'll start with a very aggressive, I would say, field sampling program from gray infrastructure, from storm sewer systems and flood control canals, all in South Florida. This is great. These are all happening in Miami-Dade County. You probably saw a couple other presentations, other initiatives in Miami area. So these are mostly prioritized area in Miami area. We're targeting 6 areas with different land uses, like residential, high density residential, medium density residential, commercial, industrial. And we will have 3 locations in each of them. So we are targeting catch basins, manholes. We are taking samples of mostly water and some sediments. And then we are also targeting 3 major canals here. Those are major canals that end up in Biscayne Bay, C6, C7, and C8 canals, and we'll have 5 sampling locations throughout each of those canals. We are trying to follow the path, and then one of our co-PIs, next slide please, they're already doing a microplastic analysis in the Biscayne Bay, so we are trying to complete that puzzle as well. So in terms of green stormwater infrastructure, we are looking at 6 different sites with 6 different green stormwater infrastructure types. So that includes a retention pond, man-made lake, constructed wetland, vegetated filter strip and wire swale, exfiltration trench, and rain garden. So again, all of these sites are in Miami area. A lot of them are in prioritized areas, like for example, C7 canal, and then the associated watershed for the C7 canal is a high priority area for Miami-Dade County and also for the Florida Department of Environmental Protection. Next slide, please. Oh, actually, you can get back. For green infrastructure, what we are doing, in addition to sampling, where possible, we are sampling surface water, we are adding stormwater, we are adding observation wells, we are taking groundwater sample as well, but we are also heavily instrumenting these sites with different sensors to look at the performance of these systems. We are creating dashboards where we can access the data in real time, and the goal is to see how we can see the performance of these systems. Next slide, please. One of my colleagues, Dr. Vatanka, is also putting together bench scale and column scale laboratory studies to look at the fate and transport of microplastic with the presence of other emerging pollutants, including PFAS. Next slide. Then we'll send our samples to multiple labs, including the analytical lab by Dr. Gardinelli. They are already, again, doing microplastic analysis from samples in Biscayne Bay, and they're taking care of our samples in this project. Next slide. And then in my lab, I'm also looking at the particle size and morphology of the particles. Next slide. And then again, the goal is to put together a kind of big database, be able to use that for developing our AI tools. So the goal is if we can use our morphology data to come up with the characterization of our particles. And again, we are relying on all the data that we have been able to collect in this region. Next slide. And another planned tool here is a data-driven decision support tool. So this is a tool that is able to help us with predicting the performance of green stormwater infrastructure based on our observations in this project and all the other available data from our other projects in the same region. Also, another thing that we are looking here, which is basically building on our past studies, mostly by Dr. Cinto, my colleague here, is to look at the performance of our flood control canals to see how we can optimize the performance of these canals for basically minimizing the discharge of microplastics to the Biscayne Bay while providing the flood control or while meeting the flood control objective of those canals.
I apologize for interrupting. I'm going to ask that you wrap up real quick.
Yes.
Oh, perfect then.
Yeah,
we're going to move on to questions.
We will have an education and extension program by the Florida Sea Grant, and we'll be also promoting the use of our developed tools. So I thank you for your attention, and I'll take questions.
If you have online questions, you can put them into the question box and we will get to them. We have some in-person questions as well.
Hi, great presentation. I would love to hear more about the education and outreach that you're going to be doing for the project.
Okay. Thank you for giving me some additional time. The bad news is I'm not doing that part. Well, that part is being done by Dr. Anna Braswell from Florida Sea Grant, and I think you have a good person right behind you, Dr. Maya McGuire. So a lot of work that Anna is planning to do here is based on the work that has been already done by Florida Sea Grant, the website that they already have. So we are gonna, improve that platform, and also, again, the outreach program will be both will be focused on microplastics plus green stormwater infrastructure and the connections. And as part of the plan, we are following like the idea of training the trainer. So Anna is planning to also have meetings, and have workshops for other sea grants to kind of exchange knowledge here, and also promote the knowledge that we have we will be generating in this project.
So great talk. So one question is, could you elaborate a little bit on the AI? Is that AI for the identifications using the Raman or FTIR? What is the exactly? Yeah.
Well, yeah. Again, thanks for the question. Well, the AI part is, well, we are collecting a lot of samples, and by a lot of samples, they are probably. I have the exact number in my proposal, but they are around like at least 1,000 samples, okay, from different areas with different land uses. Then we send them, we follow the traditional way. If we send them to our analytical lab, they do both FTIR, Raman technologies. They have a 2-in-1 device as well, both IR and Raman technology. Then we get our results from that lab. We also test the samples in my lab for morphology of the particles. I'm looking at particle size and also the shape of the particles. I see. And then we are trying to see in the future if by just running a sample through my lab that takes less than a minute to get a lot of information about the morphology of the particle, are we able to predict the characterization of the particle that is close to what we get from our analytical lab?
Great, thank you.
Thank you so much, Ali. Okay. So next talk we have Nathaniel Banks with the talk titled Aquatic Microplastic Filtration Device Research and Pilot Deployment.
All right, hi everyone. It's a pleasure to be here today. Unfortunately, my team gave me around 22 slides to get through in 8 minutes, so I'm going to be rushing through, but hopefully I can give you a good rundown on the research we're doing and the work we're getting on with. So next slide, please. Yeah, this is a brief summary of what microplastics are. I don't really think I need to go through this with you guys, but essentially there's a lot of them, and that's a big problem. So next slide. All right, more relevant, I guess, is what is currently being done to manage a lot of the available microplastics in the world. And largely, there's a few limitations. Things like trash trappers in like rivers, reservoirs, are not really designed to deal with microplastics usually below 2 millimeters in size, and especially not the ones below 1 millimeter in size. And ultrafiltration systems like reverse osmosis, granular activated carbon systems, they're really designed for state-of-the-art water treatment facilities and are incredibly expensive to install and maintain. So they cannot really be systematically deployed, especially in water treatment systems that are less funded. So we really want to come up with a very holistic solution that's very affordable and versatile. So next slide, please. So what we've developed in our team is something very simple. So out of our lab in Princeton, we've developed this. It's essentially a twisted wire brush comprised out of a special patented silicone that we've developed. And what's cool about it is it's ultra hydrophobic. Microplastics at a small scale are also very hydrophobic, so they really strongly stick to our filter. And it can really catch quite a lot of microplastic passively without any electricity or pumps. Next slide, please. And one thing that's really unique about this filter is probably a bit hard to see on this graph, but essentially the smaller the microplastic gets, the more strongly it sticks to our filter. So while it's not necessarily good for things above a millimeter in size, when you get down to things that are around 100 microns or below, we start getting efficacies of 70% to 90% and even higher across all different types of microplastic. Next slide, please. This glowing weird image here is one of our filters with different microplastics on it. So all these glowing things on it are microplastics in our field tank, and we're getting around a 96% capture efficacy on sub 100 micron microplastics now with our newest formulation. And we've already done a few small scale pilots of our technology in an experimental lake in Canada, where this wonderful device here caught around 500,000 microplastics from a polluted lake in a fairly short period of time in a day-long deployment. Next slide, please. So what I really want to talk about very, very briefly is two of the ongoing bits of work we're doing with the New York Sea Grant and with NOAA, one of which is the curb monitoring deployment, and the more important one I think we're to focus on is probably the Atlantic County Utilities Authority wastewater pilot. So next slide, please. So quickly on the curb monitoring, we deployed several of these pontoon devices just with our filters. These are really for sampling, just to see, does it pick up anything in the field. These are deployed at two rivers, one which was a tributary called the Sawmill River Creek, and one which was in the direct Hudson estuary itself. And it was deployed with a team of students at the Center for the Urban River at Beizhan. Next slide, please. And the data we got is a bit variable. So we actually did manage to capture quite a lot of microplastics with it. So we were finding per liter, we were getting between 100 and 300 microplastics, especially in the Hudson. So we were getting more in the Hudson than in the Sawmill River. But next slide. And we were finding most of it was generally PP, PET as well. But the issue we had was the type of deployment. So these devices we were using were not really designed for the brackish and more rough water of an estuary. So we were getting quite inaccurate data towards the end because a lot of our devices were actually getting destroyed by a lot of storm surges. So if you go to the next slide, one of our new aims for next year is to really make our devices for deployment a lot more robust. So instead of it being something that we just dock and leave and it gets destroyed by a storm, we're turning our devices now into a simple USB system that will be able to go out, survey a certain area of water with our filters, and then we can just collect the samples, reuse them. And these devices are significantly larger than what we had before. And our aim is to have 3 or 4 of these devices ready by March next year. So we're in the testing phase at the moment. Next slide. Yeah, sorry. So this is the big one I really want to talk about, which is arguably the world's first wastewater treatment pilot for removing and recovering microplastic. And this is at the Atlantic County Utilities Authority. It's this giant facility here, which is around a 40 million gallon per day facility. Next slide, please. So in this one, we came up with a design where at the very end of treatment, all of their water flows out of their facility through this narrow channel. And we wanted to get around 720 of our filters deployed in this channel to see what we can intercept. Next slide, please. We also wanted to sort of not just focus on removing microplastic, but also raising awareness of the issue of microplastics. So we designed this pavilion here to go alongside our pilot to really exhibit what microplastics are and the efforts we're doing to remove them. Next slide, please. So over the last summer, we really worked very hard to get this pilot and the full system built. There's me there with that blue hat there, helping with the assembly. And if we go to the next slide, we successfully launched this pilot in mid-September. So these are all of the filters in place. We had a senator go and do a speech for us. It was Andrew Zwicker, as well as representatives from NOAA, Sea Grant, and also many other water treatment professionals as well. So we were very happy with the turnout on the event. Next slide, please. And once we get all of the plastics on our filters, we've developed these cleaning tank systems that have around a 90% recovery rate. So if we put trays of our filters in there, it basically power washes them and recirculates the plastic into a dry sample. And we're starting to collect our first samples now. So if you go to the next slide, this is also the educational pavilion when it was finished. So we're pretty happy with how that looks. And now that's being exhibited. It had 300 student visitors currently, and it's going to get 2,000 next year. Oh, I'm actually ahead of time. All right, I'm really rushing ahead. All right, well, I'll be very slow on these last. All right, so essentially, we have now started our sampling process for this pilot. So it's been operational since mid-September, but we realistically started real sampling probably in October because we wanted to make sure the system was operating correctly. We had to change a few of the systems design. But essentially, we take samples from the brushes themselves to determine how much microplastic they're collecting before and afterwards, as well as also samples from our cleaning tanks to estimate how much microplastic can we recover. So if you go to the next slide, and this is our first bit of data. So this is the very first bit of data from this pilot that we're quite happy with. The shocking thing is we're actually getting more microplastics removed than we originally were intending to. So we're now getting around between 750,000 and 1 million microplastics per wash. And these washes were initially once per week, but we were finding our filters were saturating with microplastic within 6 hours because of just how much microplastic there was. So our new protocol is to increase the wash cycles to once every 3 to 4 times a day is basically what we're increasing it to. And for that, we need to automate our system. And one last thing is we were also getting a lot of large microplastics. So this isn't really even a microplastic here. This is like almost an inch big. So we were getting a lot larger microplastics than we were getting. So it's around 2 kilos of microplastic being removed each time we're deploying. Next slide. So one of the many things, I have 20 things I want to improve on this pilot, but this is just one thing I would like to show, is we're designing a new cleaning tank system that's going to be way more efficient in terms of water use, as well as hopefully microplastic recovery. And that's currently what we're developing, and that's going to be operational once again in March next year. Okay, I think that's everything.
We have time for questions.
I got one here.
This is a quick one. With your automated cleaning system, would a wastewater treatment facility employee need to do that cleaning, or can the system, I'm wondering how much like labor it takes to clean these things.
Yeah, that's a good question. Currently, because we already have a lot of infrastructure installed that is unfortunately quite manual, that first update, so that cleaning tank update, would still require a worker to essentially take the filters and clean them. One thing we're planning on doing, not for this coming year, but the year after, is fully automating the system. So getting it so that, once again, it can just run independently, or with at most, just a person clicking a button and it does the whole process.
This is a fantastic talk. Thank you. I'm glad I stayed to this. I'm not going to miss my flight, but it's okay if I miss my flight. Okay. So my question is, what's that brush made out of, and how long can you use it? Because I'm seeing, are you using plastic to solve a plastic problem?
All right, that's a very good question. And the answer, no, we're not using plastic. So it's a proprietary silicone. And the difference in terms of how that effectively functions is that the silicone, in terms of at a molecular level, is a lot stronger. So it won't ever UV degrade in the same way that plastic does. So it can still fragment. So we monitor these things very rigorously to see how long can these things be washed and reused before they break apart. And so far, there's been very little signs of fragmentation, but we put an estimated lifespan of around 6 months. But these things will never UV degrade into nanoscale particles like a plastic would. And that's one of the key differences.
We had an online question, but I believe you just answered it, Nathaniel.
Okay, there's a question back there, I think, as well.
Very popular.
Yeah, thank you. Really great, exciting stuff. I'm wondering, once the silicone brushes are no longer usable for microplastic removal, can they be recycled and developed into new brushes again?
Yeah. So these things are fully recyclable. It's because it's such a simple thing. You can just untwist the wire and separate the steel and the silicone from it. And we actually have we're having ongoing talks with the biggest silicone recycler in the US, which is actually based in New Jersey, so not far from where we operate. And essentially, we don't have enough to give them for them to start the recycling. But once we get, a larger production on this, they reviewed it and said it should be fine for recycling into silicone oil that can then be reused for various silicone products.
Really cool project. Thank you. I had 2 quick questions. One is, you mentioned that the majority were PET, and were those fibers or fragments? And then my second question is, your wash system seems really cool. I'm just wondering, do you then run it through a filter before the water is re-released? And then is that filter, do you have to then remove that filter after every rinse? And then what do you do with those filters? Thanks.
Yeah, so most of what we're collecting at the moment, especially from the water treatment pilot, are fibers, but we are also finding films and fragments as well. But in terms of answering that second question, that's a really annoying thing we're trying to deal with, but that's why we're getting a lot of the new design, is essentially all that water circulates onto a very fine metal screen, which we've set at around 15 micron at the moment, so it's very fine. And all the plastic cakes on that, and now the issue is how do we get the stuff off of that? So we're now designing a new backwash system that basically reverses the flow, pushes it off, gets us a very concentrated, still has a bit of water, but a very concentrated, basically sludge that comes out. And we just collected our first couple samples from that. And the issue is also, what do we do with this sludge once we have it? Because at the moment, it's staying in my office. We decontaminate it and everything, but we have it in this giant barrel. And now I'm getting very worried because now we're collecting like kilos of the stuff every day. That barrel's going to quite quickly fill up. So one of our next steps is trying to form partnerships for like, what do we do with this microplastic now that we've concentrated?
So that's why you should give it to Travis and I. Our fungus will eat it and make something.
Awesome.
Thank you. That's all the time we have for questions.
Okay, so our next talk is titled Artificial Intelligence Assisted Characterization and Capture of Aquatic, Nano, and Microplastic Debris by Kyoo-Chul, Kenneth Park.
All right, hello everyone. Thank you for staying here this afternoon, and thank you very much for giving me the opportunity to share our thoughts, which is basically based on the funding from NOAA. Today, I'm going to go over 8 slides, not 22 slides. So I would slow down, and then you would find that I would use a majority of my time to go over this the next slide, please. Over here, you can see the project overview with my team members. I am very fortunate to work with these 5 different co-PIs. You can see that the first 3, including me, we are working on the technology development, which is the far left column. And then the last 3 co-PIs are working on the middle column, which is related to the assessment as well as the community engagement. So let me try to go over that step by step so that you can understand this slide. And then the rest of the 7 slides would be about the details of our technology, okay, and the other plans related to the engagement part. So first of all, we are starting with the characterization, and that is based on the AI. So if you hear AI, probably you're interested in, and then you are a bit worried about, can I actually understand the AI? That's fine. It's not that different from some kind of fingerprint. Okay, so if we have a library of fingerprint, then we can actually identify the fingerprint if we find that one on any kind of surface very quickly by comparing those things to each other. Okay, so that is the idea of the AI-based characterization. And once we identify the specific microplastics we would like to target to capture, then we can use 3 different technologies. Please note that the far left, the bottom 3 technologies can be combined together, because if we have the actual microplastic particle capture situation, then we have a wide range of the particle size as well as chemical composition and different diameter things. Okay, so the first thing is nanoscale porous structure called MOF. It stands for Metal Organic Frameworks. Okay. And then the second one is a bit larger pore size, the sponge, like the sponge you use for the dishwashing. Okay. And the last one is you would come to know that why I have very, very cute whale over there, Beizhan. So that is about the hairy surfaces inspired by the baleen whale hairs. Okay. So once we have that kind of technology development, then we would like to go further in terms of the advanced testing at Whirlpool. Whirlpool is the #1 manufacturer of the laundry machine, and we are targeting to work with them to think about the microfiber as well as other types of microplastic particle capture problems. And we would like to also work with the community members through Illinois Indiana Sea Grant, Sarah Zach over here. Okay, so now I would like to go over the details step by step. Next slide, please. So here you can see the Lake Michigan over here. And the main message is simple. We have about very different types of microplastics, from nanoscale to the even millimeter scale or 1 inch. I'm talking about the microfibers. And if we think about the current remediation methods, they are expensive. They are non-specific, and they are difficult to scale. So to overcome these limits, we would like to introduce those 3 methods I briefly mentioned so that we can make the inexpensive and specific and easy to scale, okay? And please note that inexpensive means cost effective. I'm not saying that our materials or the filter systems would be very, very cheap, okay? If we can think about the revenue on investment part. So next, please. So here you can see our first step, that kind of characterization, because once we know our target, then we can optimize our filter systems, okay? So here you can see some kind of examples of the fingerprint of the microplastics in terms of the chemical compositions or the size or aspect ratio and so forth. Once we have that kind of data from the cell phone camera kind of very portable material or the methods, then we can compare that kind of thing with the library of many different cases. We have the team member of Vinayak Dravid, who is an expert in that kind of imaging as well as characterization. And we also have an industrial partner, BASF, which is the largest manufacturer of the plastic materials. So that is our starting point. Next slide, please. So once we identify our target materials, then we can start with the very, very challenging small nanoplastics. So you can see that this kind of star kind of structure is with a very, very small pore size. So that pore size is almost 1 billion times smaller than 1 yard. It's extremely small, right? And then we can actually control the interaction between the nanoplastics and this kind of pore structure by controlling the intermolecular forces, okay? So that's how we can think of that. And then you can see our example over here on the far right plot. That is a forever plastic material called the PFS. We already achieved a very, very high efficiency for targeting those kind of forever materials. You know, we can just tune the chemistry so that we can target other types of specific chemicals from the microplastics or nanoplastics themselves. So that's the idea. Next slide, please. And then we can move on to the bigger and bigger sized one. And then you can see the cellulose is another natural material. And we can change another type of interaction called the electrostatic forces by changing the functional groups, as you can see over here. So we can target positively or negatively charged nanoplastics or microplastics by using this type of materials and chemistry. Next slide, please. And then here is the idea about the microfiber. It's really challenging, as most of you know. When I interact with other people, some people say that, oh, I do not make any kind of microplastics. Then I ask, do you use a laundry machine? And they say yes. And I say, you make microplastics. So here you can see that baleen whales actually have a lot of problems of consuming microplastics. I try to think about the other way around, using problems as a solution. So you can see that microfibers are collected over here, and then it can be very easily removed by stirring this kind of cage, bird cage-like structure, but it is 1 inch size, okay? So using that kind of idea, next slide, please. We would like to do the advanced testing. And next slide. Yeah, please go back. We would like to bridge the gap between the research products as well as the community key users. That's actually the point of our integrated approach to solve the micro and nanoplastics. Thank you very much.
Time for questions. Okay, I have a question for you. So what is the most exciting part about going forward with this project for your team?
Yeah. So first of all, you can notice that we have a variety of different expertise, expert from the technological product to the community engagement. And then we have another key on the partner I was not able to introduce very well, Whirlpool. So we can think about the commercialization of the world-changing technologies by using this kind of teamwork. That is actually the most exciting point because I haven't had a chance like this kind of case from the NSF funding or DOE funding yet.
You may have just started answering that with your whirlpool, but me as a consumer, how could I get this into my washing machine so I don't put out those microfibers?
Yeah, so when I talk to Whirlpool people, they are aware of this kind of important problem. And then they also think that the new market is opening because of this kind of technology. For example, in EU, they have a special regulation associated with the microfiber effluent. So for that reason, they told me that they are very interested in working together with us if we can make this kind of reusable structure. Probably most of you are interested in whether this is reusable or not, because if we think about the typical the filtration systems, and maybe they are working. However, the reusability or the cleaning system is very important. As you could see the potential of that baleen whale hair structures, which you can control the another force, hydrodynamic force. And I believe that we can achieve that kind of filtration and the cleaning all together. And that can be attached to the side part of the laundry machine. That is our goal in this project. Thank you very much.
So my question is, so are you trapping in the washing machine or the drying machine or both?
Yeah, that's another very good question. Currently, our challenge is in the water, because if we think about effluent from the laundry machine, that is with a lot of the fibers inside that. And then the problem is it is clogging the filter system. So we would like to solve that kind of urgent problem first. However, for the air side, I believe that I have another type of solution. Yeah, thank you.
Time for one more quick question.
Thanks for the great talk. I had a question. I maybe just missed it, but is this more like the Cora ball that it like rolls around in the washing machine with the laundry, or does it sit at the like where the water evacuates from the washing machine?
Yeah, that's an excellent question. Yeah, I understand your point. So I'm aware of some of the commercial products which we can use in the drum of the laundry machine. Our target is not there. Why? Because that kind of product, as far as I heard from other users, they would destroy the fabrics or the clothes. Our target is to have this kind of filtration system in the pipeline from the laundry machine. Yeah, thank you.
Thank you so much, Ken. And there's a David in the chat that says you did a great job. No, great presentation. So we're on to the second half of this session, and we're going to kick off our second half with a talk titled Commercially Scalable End-of-Life Solutions for our Agriculture Field Plastic Films Used in Watersheds Draining to National Marine Sanctuaries by Jazmine Mejia-Munoz.
Thank you. Well, first of all, as a reflection of the past couple of days, my father always asked me, are we using the tax money the correct way? And based on all, I think we'd be really proud. So cheers to the team. But today we're going to focus on this talk a little bit more on plastic culture. And so for those that are not familiar, I'll draw your attention to this image. And this is what a traditional watershed within the Monterey Bay National Marine Sanctuary will look like. One of the things that you shall understand about California is that it's one of the most dominant ag states and a top leader within the United States. And within California's Central Coast, where we find 3 of our national marine sanctuaries, also a leader in that industry. And so what we see here is a mix of vegetative fields, and down here we have our strawberry fields. So this use of plastic within agriculture fields is referred to as plastic culture. And I was told to say hit it, so hit it by request by the IT team. And so as we started doing this work, we specialize in private-public relationship. The sanctuary has been doing this for the past 30 years in collaboration with the California Marine Sanctuary Foundation. And in doing this, we focus on 4 different pollutants. Today we'll be focusing on marine debris. And the way that we have observed this is through plasticulture escaping out. So we would see negative interactions with charismatic fauna. We'd see it escape, especially during the 2023 floodings. We see a lot of this plastic escaping out. And of course, each year, about 12 million pounds of ag plastic in Monterey County alone go out into the landfills. And so as we wanted to work with this, we applied on this grant collaboratively with industry and academia. And we had 2 main missions. One was to collaborate to build and refine technology to create a process that could maximize plastic collection, and 2, that can make it a candidate for recycling. And then, as I mentioned, we do work really closely with industry members. So we really wanted to create a community that could be multi-conversational rather than directive. And we'll zoom in a little bit more into the plastic that we're focusing on today, which is the mulch film. The mulch film is a thin film used to cover strawberry fields, and this has lots of benefits for agriculture, environmentally as well. It helps prevent the weed suppresses by 66 to 98%. It helps reduce water evaporation. And it's often actually legally required when you're fumigating your field, especially for a conventional strawberry field. And so as we first began, we did an assessment. This assessment is from 2019, and our team went out to a dominant water banks in agriculturally dominant areas. And what we saw was that 81% of the plastics that were found in these ag water banks were traced back to mulch, the plastic used and that you saw in the previous image. And we also saw other kinds of plastic, but given the high amount, that kind of directed our focus. And this plastic can escape through wind, it can escape through rainfall, water that flows out. And because it is so thin, we're talking about 1.25 to 1.5 mils, it can break pretty easily. So again, we collaborated with our stakeholders and together wrote a proposal. Earlier in the conversation, we were talking about, how do you bring them in? We were in the room writing that proposal, coming up with the ideas together, and that was really key to looking for practices that could be commercially scalable. And so what we proposed, we'll give a quick teaser given the short amount of time. But what we proposed and what we have been doing for the past year is we collaborated with Andros Engineering, who is an established ag equipment producer for California and across the globe, and with Flipping Iron, who is a plastic service provider. And through that practice, what we proposed and what we are implementing right now is a mechanical collection of mulch films. So rather than collecting these plastics by hand, this plastic gets collected mechanically through what is called a mega binder. This mega binder produces a giant roll that weighs about 800 to 2,000 pounds, depending on the area from which it was collected. And then that goes into a dry wash mulch processing system. Now, this system is very unique and leading globally, mainly because it doesn't use any water. It's a dry system, and through it, it's able to reduce contamination 50 to 80%. And that's actually really key, because in our surveys, we realized when we were asking, well, if it's a homogeneous feedstock and you have a good quantity of it, why can't we recycle the plastic mulch? And it was really traced back to that high contamination level, mostly coming from the soil. And so once it goes through this processing line, they're able to bale it. That processing line bales it, and then that is now a candidate for recycling. And this plastic is getting sent out for recycling outside of the United States, which kind of targets our next goal for another phase. So then we go on to evaluating, are we ready to, we can go to the next slide. And so this is very preliminary data. We do follow the strawberry system, and all of these trials are done in commercial settings. So a typical strawberry system is going to be between 9 months to a little over a year. And so a little bit of preliminary data, but we see that the mega binder, at least in these 2 fields, is performing the same as hand removal or better, which is good because that means that it's a scale and we're able to at least have the same amount of effectiveness. And I mentioned we have been working alongside with industry members. And so outside of the trials that we're conducting for this work, the adoption process has been really significant. In Monterey and Santa Cruz County alone, that adoption process has expanded to 918 acres. And in Oxnard, it has expanded to about 3,000 acres. With this being able to collect over 800,000 pounds of plastic. And our research, our outreach is very targeted. I mentioned you often won't find us in environmental organization conferences, but you will find us in a lot of plastic manufacturing conferences and agricultural events. So we often hold outreach events, and through this multi-industry collaboration, we've been able to reach over 1,040 stakeholders. And I also want to thank all of our partners, in particular, Alina, who's been really working alongside on this project, and Tanya, who's been also a really key collaborator, and a special shout out, of course, to our co-PI, Theresa Talley, with California Sea Grant. And with that, I'll open it up for questions.
Awesome talk. I promise I'm not over here just like always suspect of industry, but I was wondering, like outside of the grant funding, do the farmers that you work with or the plastic producers of the tarping, do they fund your work to develop these technologies or any of the process?
Do they fund it? No, they're not funding this grant. They do fund other things. And when the grant proposal first came out, it had a line in there that said that they wanted to target technology that had been piloted and was ready to go to that final stage of research to application. And so, in fact, I want to give a shout out to them because they started that. So the earlier version of this technology was completely funded by industry. And they were running out of money to do that. So when we came in, we then packaged it to have all of the additional research of doing the economic study, doing the survey studies with growers, and then also doing the marine debris research to see if this technology was actually being effective, and if it wasn't, how can we modify it? So now this is version 2 of the technology, and so because we're able to have that direct trials, the trials are not done in universities, they're done in the real world, in the real commercial setting. So then we're really able to get that feedback back to them. Yeah.
Thank you. Can I ask you the economics? So they have this technology, so I'm not quite sure what the money is. Is the money that you get to recycle and make money from there, or is it cheaper to implement? I'm not quite sure what the money is.
Yeah, so right now, when all this plastic is taken out at the end of the season, an average grower is going to have about 40 people picking this plastic up by hand. When they're picking this plastic up by hand, there's different individual breaking points that are occurring. With the mega binder, instead of having 40 people out in the field, that number gets reduced to 3 people, and then the machinery does the rest of the work of actually removing it. So one of the person is in charge of driving the tractor. Well, this is not that machine, this is a different picture, but one person is in charge of driving the tractor and moving it forward. Another one feeds it into the mega binder. And then the other person that is out in the field, they're just making sure that any plastic that got left behind continues to get fed in, so that it replaces down from 40 people down to 3 people to produce this technology in this process.
So there's a job issue here then? They're just saving manpower.
There definitely is a labor shortage with.
Sorry, the question I have is, so the advantage is you have less jobs then.
There is definitely a labor shortage around that, and I think that's one of the reasons why the adoption has been, more growers are willing to adopt it. But the idea too is that because you're collecting it all at once, you're having less breaking points. So then people are digging this with shovels. So rather with this technology, you take it all at once and you never break the plastic. So now it's all collected at once. And It's kind of early for us to do it because, like I said, the first strawberry season is just coming up. So literally last week we were out in the field collecting our samples. But just anecdotally, we are seeing less plastic staying behind. And again, it's rather than breaking it at every point to try to take this piece out and another piece out, they take it all out at once with the machinery.
Thank you, co-project. We are going to move on to our next presenter. That's all
Thank
the time
you.
we have.
Okay, thank you so much, Jazmine. So our next talk is titled MOLLUSCA, a snail-inspired robot for efficient marine microplastic removal. And this talk will be by Maha Haji and Jacob Anderson. The stage is yours.
All right, so hi everyone. My name is Maha Haji. I'm an assistant professor at Cornell University, and I'm here with Jacob, who you've already seen in a couple of these, who's really involved with our outreach efforts. Before I talk about our project, I just want to say it's really great and cool for me to be on the stage, because I was actually on the stage as an undergrad funded by a NOAA research program, the Halling Scholar. So it's kind of cool to be on the other side of research now as a PI of one of these projects. So next slide, please. So the goal of our project is to really develop a microplastic collector robot named MOLLUSCA that takes inspiration from the way that snails filter feed very efficiently particles on the surface of the water. In our project, we have 4 main objectives. One of the first ones is to take what we've seen in the laboratory setting on this filtration process and scale it up and understand it a little bit better in terms of how to make it efficient in a robot. Then we plan to actually develop some autonomy algorithms so that robots can work together and coordinate their plastic collection efforts to try to maximize concentration. And from there, we're going to scale up to actually a full-scale robot and do some field testing of a group of these robots out on a lake, Oneida Lake at Cornell Biological Field Station. And then finally, throughout this whole theme, we have a lot of outreach and community efforts that Jacob will talk a little bit more about. And I want to highlight that this is very much a multidisciplinary team. Myself and Sunny Jung at Cornell, who couldn't attend today, are the PIs, and then we're supported by a number of other folks at Cornell as well as New York Sea Grant. Next slide, please. So as you're probably all well aware by now, the current methods of plastic removal are really inefficient in many different ways. Some of the examples I've shown here have challenges such as high fuel consumption, ineffective at capturing microplastics, they have high operational costs, and they have difficulties handling various environmental conditions out in the ocean. Next slide, please. Our solution is inspired by snails, and the picture you're seeing on the top is a look at, from the bottom up, of a snail's undulating foot. It actually undulates to bring in particles that are, in some cases, 10 times away, 10 times its diameter, body length away, into its mouth to very efficiently filter feed. So Professor Jung at Cornell, his group took inspiration from this and actually built a lab scale version of this foot that undulates like a carpet. And so that's what you're seeing down here. And so they're actually doing some work to analyze how can we make this process efficient, what kind of frequencies and amplitudes make sense, what kind of motors can we use to make this really, really low energy efficient for filter feeding. Next slide, please. And then from that, we're actually building a lab scale robot to work around that filtration system. And we're really highlighting building this robot for autonomy and collaboration, because we think another one of the big drivers of the success of this project will not just be one robot on its own, but the ability to group robots together and to smartly engage them to potentially concentrate plastics in certain areas, to maybe also sense where plastics are concentrating and redirect efforts. So this is a mock-up of the lab scale developed robot that's under development right now by Kirsten Peterson, who's a co-PI on the project. Next slide, please. And then from there, based on how our lab scale tests go, my group will actually be developing this into a much larger scale robot that's fully renewably energy powered. And we're going to be integrating a novel sensor that's under development by Dr. Anna Michel's group at Woods Hole Oceanographic Institute that's able to do really efficient detection of microplastics versus biology and organic matter so that we don't have any bycatch. Next slide, please. And then, as I mentioned, we've got a lot of outreach efforts throughout this whole project. So I want to turn over to Jake to talk about this.
Yeah, so I'm not the only person from Sea Grant on this. So is Nate Dragg, who some of you may know. He's our Great Lakes Literacy Specialist from New York Sea Grant. And he'll be running and facilitating the teacher engagement aspect of this. So in the summer of 25, he'll be hosting a teacher workshop, which will be 25 teachers across New York State getting together for a 2-day workshop and kind of putting together a curriculum based on this project. And each one of them will get, in theory, a miniature model of this robot to plan and create a curriculum to go back to their class and to do outreach on. And then in the following years, they'll host 2 more teacher trainings in each state. So there's 2 in 2025, or 2 in 26, and 2 in 27. So there's 125 total teachers. Next slide, please. And then kind of footed more by myself will be some community outreach over the course of the project, attending 12 different outreach programs in order to create outreach material itself and just get the community more aware of microplastics and using these miniature model robots kind of encapsulate and show them exactly how the machine works and how to be involved. And then also still in the process of building out a steering committee. We're figuring that out along the way as we go. That was it.
Can we take questions from the audience now?
Do you want to go first? All right. So I have a quick question about, I'm curious about how does the mechanism work in terms of proximity? Like how close to your device does a microplastic need to be before this undulation motion actually helps attract it towards your device? And also, how does it function in very high turbidity environments? So if you're like in the middle of a lake or in an estuary where there's quite a lot of bigger waves, would that interfere with your mechanism?
That's a great question. So from our initial lab scale test, we think that we might be able to collect particles as far as 10 body lengths away. So whatever the size of our undulating carpet is, 10 times that away could maybe be our limit. That's still something we're exploring right now in the lab. I should mention we are a new round of funding, so we just got started. In terms of how is it going to work, in a turbid environment, also a great question. That's part of what we're going to be analyzing. We're actually going to be putting these robots in a wave tank at Cornell and actually see how well they perform in actual wave and turbid conditions.
Thank you for the presentation. It's really interesting, and I hope my question doesn't seem not very smart because you guys are so smart. But when you have a sensor that can tell the difference between microplastics and biological matter, how does the mechanism that's attracting the pieces differentiate what it's collecting?
Yeah, that's a great question. At the moment, what we're thinking is that it will still try to bring the particles to the robot, and then we'll probably have some sort of smart track that opens or closes into a collection unit if the item is microplastic, and it will let it bypass if it's not. But that's still something that's in the works that we're figuring out.
Hi, thank you. Great presentation. I'm sorry if I missed this, but what is the size of microplastic that it is targeting, or like how small?
At the moment, we're targeting about 5 millimeters and in that range.
Do you have any other questions? For the activities with the students, you said you're going to be giving the teachers models of the robots. So are the students going to be in robotics classes at all to learn to build the robots, or is it just more so on the operation side, learning to operate them and become more aware about the issues of microplastics.
So what we're hoping is that in the curriculum we develop, the robot will be entirely 3D printed. So we will give the CAD files to any classroom that has capabilities to 3D print. We will also have step-by-step instructions for how to put this model robot together, so any student in the class could do it. And we'll also have the code already pre-built, so that all people have to do is actually upload it to a little microcontroller and connect everything together. We're aiming it for both middle and high school students, so we think it'll give them an introduction both to a little bit of making, a little bit of electronics, marine robotics, and then the challenges that we're facing with plastics today.
Okay, that sounds really cool. And with that, we are at time for questions. Thank you.
All right, it's time for our last talk of the day, and Beizhan is gonna take it home with the talk titled Precision Plastic Waste Cleanup and Monitoring, AI Enhanced Solution for Sustainable Waterways and Ocean Health.
Thank you. Since I'm the last one, could I get more time? Okay, so basically, yeah, we call this one called a P catcher, and this is a model, like with 3D model. I'm going to explain a little bit. And so I'm with my colleague Catherine from New York Sea Grant, and so the next slide. So this research idea was actually coming out from the Middle Reach, marine debris. There was consortiums, and there was a talk from EPA that said, they're showing this B plant right there, the C beam they used from the Delaware River, and you can see there are clearly a lot of these trees, leaves, etc., and also maybe dead fish was actually there as well. So there was also bottle there. So when I look into that, and they said that, okay, that takes a lot of time to do the maintenance and bring back and then they sort it out, I think, well, this system definitely needs to be improved. So that's why we, also looking into the other place, for example, the plot D there is a Mill Wheel, which is not far away from Baltimore. And you can clearly see there was a lot of the plastic, but also mixed with quite a lot of this a biomass, and which is we don't need to collect it. And also in the plot C, this is just showing in the previous plot. This is from the ocean cleanup, and then you can see there was a lot of the biomass in there. And plot A shows that actually in the Bronx River Alliance, and you can see that's quite a lot of this is actually straws and a lot of these leaves as well. So based on I talked with the Will Mill, and they said that if we can identify plastic only, they can save the effort about 60%, which is completely if we really want to be sustainable, we really need to figure out a way to do it. So that's why I put in this proposal. Next slide, please. So basically, we are going to developing a collection system with high sensitivity and specificity, using camera systems and for removing plastic and other hazardous waste from waterways. And the second is also we want to stress test in the Hudson River and also the Bronx River. The third part is actually we collaborating with industry partners and also from non-profit organizations like the Ocean Cleanup and the Wheel Mill, and try to basically potentially do the technical transfer because they really want this one. And this time we goes to the a Micro 2024 in the Spain. I talked with the Ocean Cleanup. They are really said that they want collaborating with on that. The fifth one is developing the implement education and outreach activities for consumers, policymakers, industry, etc. So please keep going. Next slide. So what next slide, please. Also, so far we got the team formed, which is we hired this postdoc Biwo Kim, and also we purchased a high performance computer for the AI, and also we started all the cameras and other materials. And this is the pontoon that we are looking into that can be, can have a capacity, which is basically I'm going to show you this one here. Just a minute. Yeah. So basically this, yeah. So this one basically is the, the pontoon that we have, so we have the solar panel on the top, so we can have the, power being used. And then the one we can do this, we can do is actually, this one have the front camera. This
Come
front,
forward a little so they can see.
okay.
Yeah,
there you go.
Sorry. We have this front camera that this is the boom, and the boom can open, but when there was a larger tree logs comes in, and there was a lot of this kind of other let's say big a dead peak. What do we know, right? So it can hit our a sensor. So what we do is actually we close the door. And so when that was not there, then we actually opened. And when we opened, then we're also looking into upfront to see what kind of items flowing down. When there was some items that we can collect it, then we start to activate the system. Because most of the system during the time we need to save the energy, we let them idle. And then we, when the items coming down, then we actually can, we have the two camera systems here. One is hyperspectral, one is the RGB camera, so we can actually do the scanning on the floor, on the flow. And so the material comes in, and then when we get the camera, we got the signal, then we identify using the AI system to see whether it's actually plastic or something else. If it is plastics, and then we actually open the sounds good. We have the small gate here, so we let the plastic flow through a west net down here. And if it's not plastics, if, for example, dead fish or tree leaves, we actually close the gate, so it actually goes back to the mainstreams. The system will have itself will be able to giving us the data real time, so we can use in satellite connections, and so that's what we are trying to right now do. Next one.
Beizhan, how big will this be?
Okay, sounds good. So we have this is about 12 feet wide, a length, and 8 feet wide. So the boom also something like 12 feet, something like that in that range. Yeah. Thank you.
Oh, is it my turn? Yeah, that was our frequently asked question when we did some outreach about this. So these are just some photos from an event we did recently, Lamont, Colombia. They had an open house, thousands of visitors. We probably talked to hundreds of people.
Probably more than 800.
No, okay, well. So the 3D model was really helpful, to your point. The kids loved it because you can kind of pretend it's a fish. And kids at this point are very aware of what cameras are. And so once they saw, I would ask them, what do you think this is? And they'd be like, it's a camera. And then one kid was like, what if a turtle eats plastic? Will the camera be able to see the plastic inside the turtle and take the turtle? So there was a lot of engagement with the technology. A leg of this project is developing education materials around plastics. I think my role will be more like leveraging what's already been developed and finding ways to disseminate that. I've heard so many different curriculums being developed and toolkits this weekend. I'm very interested in how to kind of cross collaborate and disseminate those toolkits. I don't think we have that much else. This was just awarded, so very much the beginning.
We'll take questions from the audience.
Great presentation. Quick question, how would you train your AI model to differentiate between plastic and other objects?
So that's why we have so many collaborators, because they're going to collect in the waste from the rivers for us. And then we get it, and then we're training using our camera and also hyperspectral camera to get the signals. And also we can categorize and log them, and then we use the AI to solve the problem.
So you basically take a lot of pictures from the samples that they collect, and then you use that.
Not only pictures, but also the spectra. Basically, is using the chemical, a formula method to see what actual material is there. Okay. So yeah, so this is through the collaboration with a professor at Data Science Institute at Columbia, and he's expert in the machine learning.
Great.
And on the community engagement note, doing a cleanup can maybe be a little funner when you tell the volunteers that we're going to use all that trash later and take pictures of it and study it to train a model. So hosting cleanups and then doing outreach at those cleanups about artificial intelligence and how we can solve plastic problems with AI.
Hi, once again, great presentation. I have a question about, so when you collect all the plastic, well, all the plastic or organic matter, and it's passing through your system, what is the ratio of like plastic to organic that would make you decide whether to let it go into your system or outside of it?
So based on the other researchers, we didn't do that, but based on the research, 5 to 10% is a plastic only, and you have 90 to 95% it was tree leaves and other things.
But I was wondering, like, if it's going through your system, like, when would you decide, like, this is too much organic matter for us to collect, and then you would, like, direct it out of your system rather than collect it? Because I'm assuming you won't be getting just plastic or just organic.
So you mean that sometimes you have the mixtures, right?
Yeah.
So that depends on the signal. I mean, clearly, you know, like the signal, if you even have the like something like on the surface, for example, you have biofilm, right, forming on the surface, you still will get some of the, that's why we use a hyperspectral camera that can go through deep and then can really scan the surface of the plastic and identify what kind of plastic. Is that a mixture of the plastics, or is it just by the plastic itself, or is just the you know, like the biomass materials? So we're going to have the AI to get training on that as well. That's a great question. Yeah.
Thank you.
We have time for one more question.
Great talk. My question is where the computing is conducted and what computational unit you use or you place within this robot.
So that is why I have a collaborators. So we have these collaborators. He's an expert on that. So yeah, that's I don't really know that much on that. You know, like the AI system, etc. And how do the computations, how do the algorithms, yeah. But next time I will try to bring him to here, okay? If you have time.
Thank you.
Thank you very much.
Thank you. That was our last talk for the day before we go on to our workshop. So we're going to move on to a break for now, but can we get a round of applause for all of our presenters? We will come back at 3:25 for our workshop.